Hi, I'm Eric Nelson, founder and CEO of Augment, and I am with...
Hi, I'm Jody Ho.
I'm Corinne Yu.
I'm Skylar Jung, and we're students of Abby Brown's math class at Torrey Pines High School, San Diego, California.
We're presenting a vision for the use of learning tools to scale up learning environments like the Wolfram Summer Camp or computer-based math.
We worked on a piano skills visualizer, which is an example of a learning tool that aggregates, visualizes, and feeds back practice data into a student's learning path.
Okay, welcome. My name is Eric Nelson, founder of a company called Augment. We live in Minneapolis, and I work with Abby Brown's class in San Diego, California. These are three of her students, Corinne, Skylar, and Jody. Each of them have worked on a project that you're about to see here. There are also other students who've worked on this project that are not attending, Ashutosh Shah being a particular example. My job here, introducing them and their work, is to convince you that there's a golden age of mathematics education. I know I'm kind of late to the party here. Wolfram has given us a tool, Mathematica obviously, that enables students to do a lot more in a lot shorter time and with a lot less experience than they would have to do with a normal programming language. And we see a huge opportunity to make use of this technology at all levels of education, not just college, and possibly not even high school, but that's the focus right now. So I connected with Abby a few years ago now to work with their students, train them in Mathematica programming as a software development discipline, an engineering discipline, and actually develop real software, which then they go on and use in their collegiate work. And so it's all very good for the students, and we also have things that we're developing using Mathematica. One of them right now that I'm going to talk about and that they'll demonstrate is actual learning tools. Tools that we imagine will support the assessment of understanding, and of course the big man on campus for assessment of understanding is Grant Wiggins, unfortunately deceased a couple years ago. His book, Understanding by Design, has been prolific in terms of educating educators on how to assess understanding. Well, as anybody who's used normal tools, particularly in math, like Khan Academy has an excellent quizzing platform, and it's gamified, and kids actually like to use it. But we're not assessing understanding, really. We're assessing procedural skills. And the question, and I would say kind of the holy grail of using technology in education, is can we actually, from practice data, can we assess whether someone understands something? Sorry. Yeah, okay. Anyway, so we can think about the implications. The opportunity that we have here is if we have a transition between normal math class, which is lecture-based, and typically it's exercise and procedural skill focused, preparing for various tests and examinations. If we were to shift over to something like a year-long Wolfram Summer Camp, I think that would be, in some ways we can imagine that as an idealized way to learn math. It's just a continuous knowledge-making experience, using Mathematica as the tool to then manipulate math and computational thinking. And also, of course, computer-based math, which is, in some ways, that's a real instantiation in a schooling environment. It hasn't obviously penetrated more than the Estonian market. But we have a real consequence that we have to face. And this map, of course, just demonstrates that we're behind in math, blah, blah, blah. We all know that. But it's even worse than that, I would say. In many respects, all students are behind in math because, as Lockhart, the guy who wrote that essay about the travesty that we're doing with math education, many students really don't know how to transfer the math concepts to application. And so they go through years and years of study acquiring procedural skills, but they don't have the transferability. So it's even worse than this map would suggest. Now the question, of course, is scale up. How do we scale up something like Wolfram Summer Camp or computer-based math? And as John McLuhan, I think standing at this spot, except it was over there, said, yesterday, assessment. Assessment is a big problem. How do we assess these higher order skill sets, cognitive skills? And then how do we communicate that we have assessed and we are making progress and that the students are learning? It's much harder to compete with procedural skills because those are easy to test and easy to visualize various progress being made. So if we had this, I'm actually ahead of myself, and this is also, I'm ahead of myself there. So if we can imagine a tool that would show a student's capability, and we can just think about math for a moment. We'll talk about something else when these students are demonstrating. If we were to think about capability as a topology, a topographical map, or we can think about it as a network of concepts, and we can think about heat maps. We can think about a concentration of competence, concentration of experience, concentration of projects, and we would link all of this together into an application which is queryable. And as you might imagine then, if you have the intention, either as a student or as a teacher, to learn a new thing, to move someone's mind into a new space, you would have a map of their current skills and the current concepts that they understand, and you would simply be able to plot a course. And it's back to math, because many of these concepts can be related semantically, right? They have relationships in a network, the semantic web. This is, of course, how we search for things on Google. There are tools that already exist for certain subject matter. Typing, I would say, is kind of like the hello world of learning applications, because it's so easy to relate typing as an exercise to typing as a performance object. It's the same exact thing. And the data is really easy to capture because you're typing it in. But there are other things that are much harder. This is actually from, this is an AI typing tutor. There are other things that are much harder, say, for example, piano. Piano consists of both automatic skills, things like keyboarding, and also the higher order skills of composition, being able to hear music, being able to read music. So they're all different kinds of skills being represented, and not simply the obvious automatic ones. Ultimately, we would say that assessment of these higher order skills results from, and this is how we do it as humans, this is how the human brain works, we infer. So a piano teacher observes someone playing piano, and from their behaviors, from their posture, from the sound, and usually you do a kind of a gamut or what we might just call an assessment set. And from that, you infer all of these other things. But you cannot scale that. That is not something that you can distribute over a course of 10,000 students and over a course of a year, because you don't have that many experts who are able to assess. So the question is, can we develop software to do this? This enables scalable training. We can imagine a particularly good piano teacher would be able to infer and interpret the results from a whole lot of students. And then they would be able to provide the personalized feedback, which is essential, required for best growth path. Then, for the Augment side of things, we train programmers, and they themselves need to be able to infer from the evidence what each other can do. If you have a team of people, and anybody who's done any project work, you understand that if you're going to hand something off to somebody else, you need to know that it can be done and that it will be done properly. Well, that's very hard to do if you don't know what that person can do. And if you're relying on certifications and other project portfolio, there's a lot of things that can go wrong. And so really, most teams operate entirely based on their experience together. And so they get very close-knit, and they're able to interpret based on all of that experience. But if you don't have that experience, what do you do? So we're trying to answer that question. The system that we will be demonstrating, or these students will be, is a system which captures piano data, which is in a MIDI format, and it aggregates and feeds it back to the learner. And the key for these sort of systems is the signal-to-noise ratio. You need to give somebody the right information at the right time, both the teacher and the student. Then from this, our big question is, what are the edges of comprehension? How do we know that this person knows X, Y, Z concepts? What is really the subject matter that they understand from this context? There's a second tool that has actually been around for quite a while, and it actually goes back several decades in the form of military and commercial aircraft certification rating systems, actually called behaviorally anchored rating systems. We actually, an advisor for my company, Augment, Gary Jednak, is an inventor of a commercial form of what we would call behaviorally anchored self-assessment. Here's an example. Back to this idea of observing behaviors. If you're looking at somebody in a wood shop and they cannot hammer in this case, it's 6 small nails in a piece of birch without bending the nails, without denting the workpiece, well, then you would say they very likely could not make a cabinet, right? So there are strong inference behavioral indicators that we can pull from that context, and we can imagine this for all kinds of skill domains. So BASA is another way of very quickly getting to the heart of the matter. Can this person do this? Do they understand X, Y, Z things? There's a lot of background to this. I just left it there so you can look at it later. Okay, I'm out of time, so I'm going to move over to our students here. But the big question is, how can the computer be better employed to grow, express, and assess human understanding? We think that if we do a better job with assessment, we can scale up learning environments like the Wolfram Summer Camp and computer-based math, which, as I see it, brings in this golden age of math education. And also, for our purposes, it enables much better, much faster performance from high school level students who can very quickly acquire skills, work together, and like Abby was showing with her 3D prints, they can accomplish real, useful things. The proofs of various theories and experiments like the ramps. Okay, moving on. So we have Corrine, Jody, and Skylar. They'll be talking about an application that they developed to assess and feedback piano skill in a visual format.
So, as a part of Augment's programmer training, we each developed a common skill set using resources that explain Mathematica concepts and principles of computational thinking. And after we have completed this training template, we worked to create a piano skills visualizer, which provides beginner piano players with feedback on objective elements of their playing. And we used a few principles that allowed us to work collaboratively in an efficient manner. So first, we implemented what is known as Jigsaw Teams to help us manage our workload. While in the development phase, we found ourselves more invested in certain topics than others, so we just worked on parts that had the most interest to us. And we met up at the end of each week to discuss our progress in certain aspects of our project. And also, we started designing our program in English first in order to visualize the general structure of the program that we're creating before learning all the specific functions that help us to implement our ideas. And while coding, we also made sure to include comprehensive documentation, such as the designer's intent and the pseudocode, as you can see in this example we have over here, so that anyone who opens our file are provided context once they open a shared file. And another thing that we used is something called a concept domain, which is a shared language that includes a set of technical and musical language so that we can standardize our communication. This is similar to how an air traffic controller or a military unit would use a domain-specific language that allows them to be both concise and clear.
So more going into the piano project, within this project specifically, we developed the project in a piecewise manner with 2 main strategies. We first wrote simple functions that we later made more complex, and then the second is we applied these functions first to certain instances and then extended them to more general applications. So one way to develop a large project like this is to decompose it into parts, which can be combined later on. Musical sound, although artistic, can be translated into a purely computational problem by breaking it down into objective elements like timing, note value, and volume. This nicely corresponds with the MIDI file data, which also does note value, and then timestamps, which are the starting time and ending time of the note. And then next is key, note velocity. So this keynote velocity in piano players' terms is how hard you press a key. However, Mathematica reads it as volume. So in the beginning, we had a lot of difficulties generating a lot of data that were similar to how we were going to format our notebook. So we created a data generator. So what it would do was introduce errors into a perfect MIDI piece that we had. So as you can see as an example is we have the timing function from the top. And then from here, you can see we had the variation range, the number of lessons, and improvement factor. So this was just also another way of us thinking of long-term analysis, of thinking about over time how a student would improve and how this variation would become less and less. So if we go down to our data generator, this is bringing back the idea of going from simple to complex. So we have not only the timing now, but we also have note value and volume. So we have all this variation. If we look at the data generator, at the top, we have the sliders, which have the different variation ranges. And then the second, the first sound note file on the left is the perfect piece. So if we play it now, there's a little bit of a lag. And then our data generator would input some errors into it. So if we play the right one now, so you can see on the bottom, we also introduced the idea of the lesson number, which is our attempt at long-term analysis. So this was lesson number is how many times you would play the song. And then timing variation is just how much varied it would be. And then note variation and volume variation follow the same format. If you would go down to 0 variation, that means you play the piece perfectly according to the exact MIDI file. And then the graph below is also just a graph of the variations between progressively in time. So for the analysis portion, we took each of the values along the progression of the song, showing what mistakes were made when and where, which served as a strong and intuitive visualization for the computations. We'll show more of the visualization later. But then we also had to think of generating this instances to general. So we first had to hard code certain functions, such as that Mary had a little lamb piece. So that was created with Mathematica's sound note functions, where each note would be put into the program. And then while doing this, we had a better understanding of how the sound note functions worked and how to create the computations done on the file. And then after doing the functions for this piece, we had to generalize the code to be more applicable to other songs as well. So as you can see here, it's the same data generator. However, if we play the first 2 seconds of this piece on the perfect side, and then this was the perfect for if you know the song Entertainer. And if we play the right side now. So as you can tell, there's a big change between the two. So it goes this general way with Entertainer. And then we later, after this, we had to think about real-world applicability. So what we did was we imported an actual MIDI file into this program, and we thought, does our program still work? Successfully, it did. And then, yeah, it was great. Oh, and then now we have the visualization. So how we did this is we took the data generated from our program that looked at the mistakes that were made. So for the timing function, if you can see on the x-axis, it's the time interval between the songs. So from 0 to 2 seconds, that's the first quadrant. From 2 to 4 seconds, it's the second quadrant. And then we have the cumulative error on the side, and it's just counting how many times you make an error during that certain time instance. And then what the timing graph does, it also allows for students and teachers to see during what time interval do you see the most amount of mistakes, whether it be from properties of the song or from a player's just disposition on the difficulties of playing it. And then on the note graph, you see on the x-axis, we have the practice MIDI notes. And then on the y-axis, we have the perfect MIDI notes. So what this graph would show is whether a student played B instead of an A, and then what it would do was it would place a point on the XY axis, and then depending on how many mistakes you make during that song, it would go up by 1, 2, 3, or how many times you would make a mistake. So in general, if you had a perfect piece with no mistakes in the note, it would just be a flat plane.
Okay, so we'd like to see our project expand in several directions in the future. So currently, as you see, it's capable with short-term analysis, but we'd also like to extend it to long-term analysis, because in the real world, teachers would probably want to see trends in improvement along with the current playing ability. And we've started implementing lesson number and improvement factor variables to find patterns of recurring mistakes. We could also analyze more complex technique signatures. So adding these on top of the skill sets that we already have could enhance the spectrum of skill level analysis and provide better feedback for a wider range of songs and techniques. So for example, one kind of technique signature would be syncopation. And syncopation is when you intentionally deviate from the normal flow of rhythm. So this could be another factor that would be taken into account when we analyze a student's recordings. Our user interface is currently very basic, and the only way to import certain files is to, of course, call import and then specify the file location. But this might be a little bit cumbersome and difficult for piano teachers and students, especially little kids. So we'd like to implement a more polished interface that also generates our output in a much cleaner fashion. So to recap, this project was just one example of an attempt to grow, express, and assess student understanding in the piano skills context. So all of us are pianists, and we all had, this was a useful background to draw on when developing this project. But in the future, projects like this could be expanded to all kinds of skill sets in order to capture behavioral data, which can then be translated into inferential data, ultimately allowing us to predict and improve future performance. Thank you for listening.